Hello and welcome to this tutorial. Today we're going to be looking at section 3.1, impulse. Please remember to pause or rewind the video as needed. Okay, let's begin. If you read along with me, it says that a change in momentum for an object is equal to an impulse. That's what an impulse is. An impulse is a change in momentum. Now, let's just remind ourselves of the various variables and equations we've used up to this point. Okay, now momentum is the variable p. Okay, and it has a unit of kilograms meters per second. Well, a change in momentum would be delta p. That would be a change in momentum. Now, if momentum is mass times velocity, then that means a change in momentum means something changed. Either the mass changed or the velocity changed. Now, usually it's not because a mass gets bigger or smaller. It's because the object sped up or slowed down. So in other words, a change in momentum is really equal to the final momentum minus the initial momentum. But you can see because the speed changed, the momentum changed. That is one way we're going to be calculating, okay, a change in momentum. Now, another name for a change in momentum is called an impulse. The variable that we're going to use for impulse is the capital letter J. So another thing that we have here is that a force is what is done to change velocity. If you think about how that works, net force equals mass times acceleration. Well, that means a net force causes something to accelerate. And when something accelerates, it changes velocity. So this occurs over a period of time. And so we have an impulse, a change in momentum, occurring over a period of time. Force times time. So you actually have two different equations here because this could equal impulse and this could equal impulse. And so down below, let's go ahead and really break down all of our possible equations that we have for impulse. One of them is J is equal to delta P, which is equal to mv final minus mv initial. This is one equation that we'll use right there. The second one is that J, the impulse, is equal to force times time. Now, since J is equal to two different things, right here and right here, well, then it makes sense that those two things must be also equal to each other. Which means force times time equals a change in momentum. So we're going to be working with those three equations as we go through this exercise today. If we take a look at the example that's provided here, we see we have a 50 Newton force applied to a 20 kilogram mass. The cart is already moving at 1 meter per second. That's its velocity. It says the final speed is 3 meters per second. That's also velocity. And we're looking for how long, which is time. Well, since you have two different velocities, that makes this the initial velocity and this the final velocity. If you break this down, we're looking for how long this is incorrect right here. We're looking for the time, t equals question marks. The force applied is F. The mass is 20. The initial speed is 1, and the final speed is 3. Now, we're using this final version of the equation there because we have force and time, mass, and a change in velocity given in the problem. So we start off with force times time equals mv final minus mv initial. You can see in order to solve for time, you need to get rid of the force. So we need to divide by force, both sides. And that's how we get that version of the equation there. Notice it's the same equation, but instead of v final, they're using v2. Instead of v initial, they're using v1. Same thing, really. And you can see now how we're plugging in the values. Here's mass times the final speed minus mass times the initial speed divided by the force. And that would be 40 divided by 50, which is 0.8 seconds. So that's an example of what's done. Let's go ahead and try one of these from scratch just to kind of develop the problem and see where it goes from there. The first thing that I would suggest is in number 1 here, since that problem-solving box is really rather small, let's take a minute to go ahead and redo the problem-solving box for a much bigger space. Okay, so this is what we're looking for. This would be our givens. This would be our formula, which is the relationship. And then over in this far box, of course, is the solutions. So again, just taking a second to redo that box will really, really help you. Let's go ahead and annotate the question. It says a force of 100 newtons is applied to a 20 kilogram cart that is already moving at 3 meters per second. If the final speed is 8 meters per second, how long was the force applied? Well, we're given 100 newtons of force, 20 kilograms of mass. This is the initial speed, VI. That makes this the final speed, VF. And you're looking for time. There's our question mark. So you're given 100 newtons. You're given 20 kilograms. You're given 3 meters per second. And you're given 8 meters per second. V final, V initial, mass, and force. Since you're given all 5 of those variables, you're going to use the long version of the impulse equation, which is force times time equals a change in momentum. You're again solving for time, which means you're going to have to isolate and get rid of the force. Well, we do that by dividing away the force. Okay, let's go see what we're going to plug into here. Okay, so for mass, we're going to be plugging in 20 times the final speed, which is 8, minus 20 kilograms times the initial speed, which is 3, divided by the force, which is 100. Break down this calculation here. We have 160 Newton seconds minus 60 Newton seconds over 100 newtons. That would be 160 minus 60 is 100 Newton seconds divided by 100 newtons. And you can see the newtons part of that cancels, giving you the appropriate unit for time, which is seconds. 100 divided by 100 is 1 second. You could write it as 1 or 1.0. How you choose to write the solution is up to you. All right, that's question number 1. Again, remember, pause, rewind the video as you need to. Scrolling on, read number 2 along with me, if you would, please. It says a 3 kilogram ball is accelerated from rest to a speed of 10 meters per second. Okay, so we're given mass from rest means V initial equals 0. That makes this V final. So let's look at what we're given here. We're given a 3 kilogram ball. We're given V initial 0. We're given V final is 10 meters per second. Okay, what are we looking for? Well, part A, we're looking for the ball's change in momentum, delta P. Remember, change, that's what the symbol, the triangle there is the Greek letter delta, and that means change in something. B, we're looking for the impulse, part B. And then part C, it says if 40 newtons of force is applied, so we're given the force, how long? So part C, you're looking for time. So for part A, how do we find a change in momentum? Well, change in momentum is going to be the final momentum minus the initial momentum. It's really just the speed that changes, right? And then finally, we need to know that it's also the momentum is equal to force times time. But don't forget, guys, that your impulse is equal to a change in momentum. So we're going to break this down into 3 different sections. Part A, part B, part C. Part A, we're looking for delta P, so that's going to be mv final minus mv initial. M is going to be 3 kilograms times 10 meters per second minus 3 kilograms times 0, which of course would be 0. And that gives us 30 kilograms meters per second. Do keep in mind, you could write it 2 different ways, or 30 Newton seconds. Something I didn't stress earlier, but I want to point this out, that the unit for impulse, if you go back up to the concepts right here, the unit for impulse is either a Newton second or 1 kilogram meter per second. They mean exactly the same thing. Now, part B, you might recall that an impulse is a change in momentum. And since we found a change in momentum of 30, the impulse is also 30. I'm just going to write it as Newton seconds for now. Which means for part C, now we're taking that impulse and we're setting that equal to a force times time. Now we're looking for how long. So to solve for time, we have to get rid of the force. We're going to go impulse divided by force, which would be 30 Newton seconds over the force of 40 newtons. And you guys can see, hopefully, that this unit of newtons cancels with that unit of newtons, giving you the appropriate unit of time, which is seconds. So the time is going to be 30 divided by 40, which would be 0.75 seconds. All right, question number 3. Read it along with me, if you would, please. A 2,000 kilogram car, that's the mass, uses a braking force of 12,000 newtons. That's the force to stop in 5 seconds. That's the time. So we're given 2,000. We're given 12,000. We are given 5 seconds. Okay, part A. What is the impulse? Part B. What is the change in momentum? And part C, what is the initial speed of the car? All right, here we go. So impulse, notice we're given force and time. That would be a good place to start. Impulse equals force times time. But recall, impulse is also a change in momentum, and that is equal to mv final minus mv initial. So we'll go ahead and break this down into a few different parts. Part A, Part B, and Part C. Part A, we're going to go force times time. The force is 12,000 newtons times 5 seconds. And we get 60,000 kilograms meters per second. Okay, now part B, the change in momentum, is the same as the impulse. So it's also going to be 60,000 kilograms meters per second. Okay, now to find the initial speed of the car, here's what we're going to have to do. We're going to take that equation, this one here, J is equal to mv final minus mv initial. Now keep in mind, we're stopping the car in 5 seconds. You know what we do? We set the final momentum equal to 0 because the final speed is equal to 0. Something I didn't note there. Okay, we're looking for the initial speed, but the final speed comes to 0. Means the equation really is J equals negative mv initial, and we're solving that for VI. So to do that, of course, we would divide by negative m. Okay, now a couple things I wanted to keep in mind here. The braking force, of course, would be friction. Friction is a negative force, which results in a negative impulse. Okay, meaning a negative change in momentum. You're reducing the momentum. So this is actually a negative J if we're throwing that in there. So V initial is equal to our negative impulse divided by our negative mass, which end up canceling. So negative 60,000 kilogram meters per second over a mass of negative 2,000. You guys can see that the kilogram part of the unit cancels, giving you the appropriate unit of velocity, which is meters per second. The negatives also cancel. And 60,000 divided by in there, so 60,000 divided by 2,000 would be 30 meters per second. Question 4 tells us that a 60 kilogram high jumper, so there's the mass, lands on a mat after her jump. The mat brings her to a stop after 1 second. Right, there's the time. She was traveling at 5 meters per second when she landed on the mat. Note, the speed of the jumper at the top of her jump before she started to fall toward the mat was 0 meters per second. Also something to note, that she comes to rest afterwards, which means V final also equals 0. That makes this V initial. Because we don't care necessarily about what her speed was when she started her jump. We care about what is her speed before landing on the mat and right after she lands on the mat. Well, after she collides with the mat, her momentum drops to 0, which means her speed drops to 0, which means V final comes to 0. Part A, you guys are looking for the change in momentum of the jumper. Part B, you are finding the force applied, okay, by the jumper on the mat. Okay, we're given a mass of 60 kilograms. We're given that V initial equals 5. We're given that the final velocity comes to 0. And we're given that this occurs in 1 second. Okay, so the impulse, which is the change in momentum, is equal to mv final minus mv initial. But we're also given that the impulse is equal to force times time. And we're going to break this up into 2 parts. So part A, the change in momentum is going to be mv final minus mv initial. Okay, and we're going to reduce the final momentum to 0, and so that's going to be negative mv initial, which would be 60 times 5, or we could say the momentum decreases, okay, by 300 kilograms meters per second. That is the impulse experienced on the jumper by the mat. Okay, now the force that's felt, okay, is also going to be negative because J is equal to that delta P, which is also equal to force times time. And so we're solving for force. So we have to divide by time. Force is going to be the change in momentum divided by time, or negative 300 Newton seconds. I'm just going to change the unit here to make it easily to cancel. Divided by the 1 second. See, that part cancels. And the force applied on the jumper would be negative 300 newtons. The negative just means that if the jumper applies a force of 300 newtons on the mat, that means the mat is applying an equal but opposite force of negative 300. It means 300 newtons, but in the opposite direction. That's all the negative applies. Number 5. A 0.5 kilogram, there's the mass, soccer ball is kicked with a force, 50 newtons, for 0.2 seconds. That's time. The ball was at rest before the kick. V initial is 0. What is the speed after the kick? We are looking for V final. Just take a moment to list everything we annotated at the top. Okay, since you have all 5 variables involved, we're going to be using the larger version of the impulse equation, which is force times time equals a change in momentum, mv final minus mv initial. Now you're solving this equation for v final, but do keep in mind that since v naught is 0, mv final is going to come to 0 as well. So force times time equals mv final. And I don't know why I highlighted that. I'm sorry. We're solving yeah, we are solving for V final. Okay, we have to divide away the mass in order to isolate that. So force times time divided by mass. It's going to be 50 newtons times 0.2 seconds. Divide that by a half kilogram. Well, 50 times 0.2 is 10. 10 divided by a half is 20 meters per second. Question 6. A baseball player hits a .55 kilogram fastball, that's M, traveling at 44 meters per second, that's V initial, into center field with a speed of 50 meters per second. So this is the speed it leaves the bat with. That would be V final. Now, one thing you guys are going to have to consider is it's coming into the bat in one direction. means it's going off the bat in the other direction. That means one of these two speeds has to be negative to account for that. And we're going to make the initial speed coming in positive and the final speed negative 50. The final velocity, that is. The impact lasts for 0.0045 seconds. That would be the time. What force? We're looking for a force. Okay, so let's list everything that's given. 0.155 kilograms. V initial is 44 meters per second, meaning V final is negative 50. Remember, the final velocity is negative because the ball is going in the opposite direction that it came into the batter with. And then the time is 0.00450 seconds. Again, all 5 variables are present, so we're going to use the longer version of the impulse equation. Force times time equals a change in momentum. Now, in this particular situation, you cannot cancel anything. You're solving for force, and the way we're going to do that is we're going to divide away the time. So let's go ahead and copy that equation down one more time. Divide away the time and substitute. Okay, mass 0.155 times final velocity, negative 50, minus mass 0.155 times final velocity, times initial velocity, 44, divided by a time of 0.00450 seconds. Okay, so breaking this down, when we multiply those, we get about negative 7.75 Newton seconds minus, and then if we multiply those two, we get about 6.82 Newton seconds. Okay, and this is all divided by 0.00450 seconds. So subtract those and divide by 0.00450, and we get a force that the bat hits the ball with a negative 3240 newtons. Now, what does that mean? Well, the ball hits the bat with a force of 3,240 newtons. The bat hits the ball in the opposite direction, hence the negative. The negative just means equal but opposite force. And in our final question, question 7, Tom Sawyer launches his 180 kilogram raft, there's mass, on the Mississippi River by pushing it with a force of 75 newtons. There's the force F. How long? T is question mark. Must Tom push the raft to accelerate it to 2 meters per second? Now, since it didn't tell us an initial speed to begin with, we do have to make an assumption that there's an initial speed of 0 starting with. That makes this the final velocity right there. So we are looking for time. You are given a mass of 180 kilograms. You are given a force of 75 newtons. We are given an implicit information about the initial speed being 0. And the final speed we are given as 2 meters per second. Again, all 5 variables present. We're going to use the long version of the impulse equation. Force times time equals a change in momentum. You're solving for t, which means you're going to take that equation and you're going to isolate it for time by dividing away the force. And substitute. Mass times velocity minus mass times velocity divided by force. Let's go ahead and plug in. Mass is 180 times the final velocity, 2, minus mass times velocity, 180 times 0. So that whole part comes to 0, which is nice. Divided by force, just 75 newtons. Now, what this gives us is time is equal to 360 newton seconds divided by 75 newtons, and that gives you about almost 5 seconds. Takes them almost 5 seconds to push it from rest to 2 meters per second. All right, I hope you found this tutorial to be helpful. Again, please remember to pause or rewind as you need to.